this might be the, science fiction movie geek in me asking you, so I apologize in advance. But I wanted to talk to you about time travel.
Okay.
Now, you have these movies like Interstellar and stuff where people are like, and I think I read this online. It might be from the movie, but it might be online where I read it. But I heard somewhere where it's like, if you go near a black hole, time changes or something like 1 year on Earth. If you're near a black hole or you're going through a black hole, it's like 80 years or something like that. And like, I wanted to know about, is time travel possible, or is it very theoretical, or what is that whole shebang about?
Yeah, that's a great question. There are some aspects of time travel which are very simple, and there are some aspects which are more complicated. So in a way, let's talk about kind of the simple thing. You're sitting across the room from me. We're separated by, let's say, 1.5 meters, 2 meters. It has taken a certain number of nanoseconds for light from you to travel to me. I'm not seeing you as you are now. I'm seeing you as you were in the past, right? Nanoseconds in the past.
Yeah.
When we look at the sun, we're seeing the sun as it was 8 minutes ago. It takes that long for light to get here. So being able to kind of time travel, not necessarily in your body, but to be able to see things as they used to be. We do that all the time. But of course, you and I, we feel like we're just in the same time, right? But astronomy is very much about seeing the past, because we look out so far away from Earth that it can take millions or billions of years for that light to have traveled to us. So, for example, the James Webb Space Telescope is looking for objects which are so far away from us. It's taken so long for the light to get here that actually we're seeing them as they were shortly after the Big Bang. So even though the Big Bang happened 13.8 billion years ago, we can still see it today because you just have to look far enough away that it's taken that time for light to get here.
Oh, wow.
Right? So everything we do in astronomy is a kind of look back. Now, some things are close by the sun. We don't talk about the sun. We're seeing the history of the sun. It's 8 minutes ago. That feels like, and of course on Earth, we're used to the fact that we're sitting here in Delhi. It's kind of lunchtime, mid-afternoon. The people in Europe are just getting up. The people in Japan are beginning to go to, they're having their evening. So that kind of desynchronization, we're kind of used to that. But not really used to it when you talk about billions of years ago in the past. It's like opening up a textbook and seeing pictures of, ancient India or ancient Rome and saying, oh, look, we can still see that. But we're seeing a living movie of it. It's not just a painting in a book, right? We're seeing things happening in the past, and it's taken that time for light to get here. Now you would say, okay, what does that teach me? Well, the universe was different when it was young. So we actually see that galaxies look different. The very distant ones, they look quite different to the ones which are around us today because they've evolved, they've changed over cosmic time. So in that sense, time travel in a kind of a sense of being able to look back, we do that all the time. Now this thing about time travel where, black holes and so on, this is Einstein's world. This is special relativity and general relativity. And if you posit that the speed of light is finite, which it is, that it takes some time for light to travel from A to B, then there's all sorts of consequences that Einstein and other scientists worked out more than 100 years ago, called the theory of relativity. And if I travel super, super fast, if I accelerate at a high speed and go out close to the speed of light, in my reference frame, my clock is ticking just as it ever was, right? Time doesn't slow down at all for me. I'm watching my watch. It's 1 second per second. It's time for tea. It's time for light, all the same. But you, looking at me back from Earth, if I've gone off, you see my clock very differently. You perceive my clock going much more slowly. Now, you can't actually perceive it in the sense because I've gone off so fast, the signal's coming back. It gets a bit more complicated. But if I go out there for a couple of years, close to the speed of light, and then come back close to the speed of light, then, yeah, indeed, a century could have passed here while just a couple of years passed for me in space. So in that sense, if you like, that's a way of visiting the future, right? But it's non-causal, by which I mean I can't affect time travel is often the paradox of time travel is often in the other direction, going backwards, right? If I just go out and come back in the future, that's possible.
Okay.
Going back into the past has a whole different, problem with it, right?
Okay.
Because if I go back into the past to just when we started this, this podcast, and one of the cameramen, we call somebody up and say, you've got to run out into the street now. We changed the whole dynamic of the way the podcast works, right? I changed the history from there on. So that kind of interfering with the past stuff, and killing your own grandfather kind of thing, so you're never born, the paradox of, well, how do you ever go and kill him? Then he's alive again, and then you're alive, then you go back and kill him. So those sorts of paradoxes are not allowed in physics. But the thing you mentioned in particular, going near a black hole, that's gravity, which is changing. It's effectively stretching space-time. So everybody knows about space, right? This around us, up there. Everybody knows about time, the thing on the dial. What most people don't realize is they're actually the same thing. They're linked to each other. We don't talk about space, and we don't talk about time in physics. We talk about space-time. And that's because if there's gravity in a certain location, a mass, a black hole or even a planet, that changes the fabric of space-time, and it changes the flow of time relative to other places.
Wow.
Right? So this is what interstellar posits, right? You get close into the gravity of the black hole, and you get too close, and suddenly everything's changed on the other side.
Wow. But could a human being actually survive going through a black hole, or would he just get torn apart?
Well, yeah, there's this thing called spaghettification, right? Kind of cool thing, right? If you get close to a small black hole, so the strength of gravity increases as you get closer and closer to the black hole. And if you're in a small black hole, the rate of change of gravity over a certain distance is very high. So effectively, you get stretched out, right? It's not like a Willy Wonka thing, right? Where, you've eaten the wrong sweetie and it stretches you out into this gummy band, right? And that, of course, disrupts all your molecules. That's not, you don't come out of that looking so good. But here's the weird thing. If you get close to a supermassive black hole, so even bigger, the radius over which the gravity changes there is much larger, and you don't get spaghettified in the same way. So you can actually, in principle, survive a fall into a very big black hole, which is what happens in Interstellar. Here's the weird thing, though. For you journey into this black hole, and everything's kind of cool, and you're motoring along in your spacecraft, and that's all nice. And you fall past the so-called event horizon, and you don't see a difference at that point. You're happy. People on the outside see something completely different. As you move towards the event horizon, everything seems to slow down and slow down and slow down from their perspective, to the point you never actually cross that limit. You never actually cross that line. You're stuck on it forever from their perspective. And so that asynchronization between how space and time work locally and in a relative sense to each other is actually, it's real. And you might think it's all abstract as well, right? What do I care? Well, you probably have a mobile phone and you use the GPS on it to navigate around. The GPS is the American system, Galileo, the European. Now, these satellites in orbit, they have very accurate clocks on them. So these clocks, essentially, by sending time signals backwards and forwards to your phone, and from three or more of these satellites simultaneously, the time differences help you work out where you are, right? The satellites know where they are, and they send these time stamps, and so that's how it works. But they're at quite a high altitude above the Earth. The gravity's different there.
Okay.
And that means they're actually in a different time frame. And they have to correct for that. They actually actively have to correct, knowing general relativity, they have to correct the timestamps they send out for where they are in Earth's gravitational field, because we're in a different part of it.
Yeah.
So if general relativity didn't work and you didn't put those corrections in, you'd crash into every second building or drive off the bridge because you would just be in the wrong place. So it does have very practical implications in real life.
Wow.